Good evening, everyone. Hope everyone is staying safe. I'd like to thank Skill-Lync first for the opportunity to talk about electric motor design. I think I'll try my best to kind of dissect electric motor into pieces and take you guys to the lowest level of design possible. But before starting, I just wanted to kind of give you an overview on how electric motors are kind of used in the industry right now. So there are automobile industry that covers electric bikes, cars, and all that stuff. And then there is industrial machine tools, for example, the machine tools that are used for shaping a metal or bending it or cutting it. So all those machine tools use different sort of servo drives and electric motors in different applications. And there are different types of electric motors that are being used currently, but the whole electric motor design has started with a DC motor, which is the basic electric motor that works with DC voltage. And then there's AC induction motor. That was the inception of AC motors, almost like wireless power, if you can say. And then there are permanent magnet motors, which are more popular these days. They're helpful in generating higher torque, higher power density, so that they became very attractive for electric cars and hybrid electric vehicles, um, and even electric bikes that you're seeing right now in the market. So industrial machine tools have multi-axis operations. So you have a gantry system or an XYZ system that operates in 3 axes, and also robotic automation, which has several axes. So the motors kind of work as a coordinate system in those applications. And there can be several different types of motors which act together. So that's how electric motor is being applied in automobile industry and industrial machine tools at this time. However, I think electric motor design in general has evolved so much that it has become a very efficient design. You hardly see failures in electric motors nowadays, unless if it's put under really high torque loads or overburden the motor, you'll start seeing some short circuit currents or etc. faults, like earth leakage faults, for example. So that's why I think the next generation of motor designs are designed for higher reliability so that they can last for a really long time. And then they also give you higher efficiency, which means more return on investment on the electric motor. So the lower cost is obviously an attempt to reduce the material costs that are used for designing an electric motor. So that's where the design of electric motor comes into the picture. So there are several multinational companies that offer that are designing electric motors in this world right now. So to start with, I think Toyota's hybrid Synergy drive has a really specific electric motor design that they use. Um, I'll speak a little more about Toyota's 2006 Prius electric motor down towards in the presentation. But Nissan has Leaf, pure electric vehicle. They have their own motor design. Tesla started with an induction motor design, and then eventually I think they have gotten into permanent magnet motor designs as well. Chevy Volt is a pure electric vehicle. They have their own motor design. Apart from automobile manufacturers, the electric motor manufacturers that are commercially selling these electric motors obviously put in a lot of R&D into developing next generation electric motor designs. Some of the most famous electric motor manufacturers around the world are ABB, Siemens, and Nidec, Toshiba, WEG. So these companies are kind of the market leaders in electric motor manufacturing industry. I just wanted to give a different section of servo drives. So these drives pretty much come as a combination of drive with the motor. So Yaskawa has a drive and a motor package. Panasonic has one. Beckhoff, Schneider Electric has one. So these can be considered as industrial standard designs. That's how most of the industries look for. They don't want to buy a drive from a different vendor and a motor from a different vendor. They'll choose to buy a package. So these companies have evolved into developing such motor drive technologies that are used in the industry right now. There are some other companies. Obviously, NASA has designed some specific electric motors that work with, you can say, a lunar robot or a Mars rover. Their electric motors withstand higher altitudes and higher pressures. So there are several design considerations that go into electric motor design when you consider altitude and temperature and pressure, all that. It's like environmental stuff when you're designing electric motor. General Motors is another big company. LG is one of the big company. Even the washing machines that they have designed, I know that they have designed switch to reluctance motors that are efficient and that can be used in washing machines and other home appliances that they sell. Some companies in India, I think Tata and Mahindra Rise have spent enormous amount of effort in designing autonomous vehicles. I know that they're doing research right now. So one of the major component of autonomous vehicle is the electric motor. The motion has to be optimized. So they are spending a lot of effort in designing a cutting edge motor drive technology for that works with automobiles. But I think Bajaj, TVS, and Hero have spent time into electric bike designs. I think they have started coming out with some basic models which are pure electric. So most of the electric motor designs that are used in these electric bikes are mostly in wheel designs, so that the motor can fit in wheel and doesn't need extra powertrain or extra transfer of transmission stuff. Some Indian electric motor manufacturers are Havels, Crompton Greaves, BHEL, Bharat Bijli. One of the interesting notes, I've known a friend who worked in Crompton Greaves. So one of the interesting projects that they have worked on is designing BLDC motors for Indian Railways. So Crompton Greaves, I think any motor that you see in a fan in any Indian railway, I think is probably designed by Crompton Greaves, and government probably contracted that design to them. Some of the leading software providers in electric motor designs start with ANSYS. I think ANSYS is probably the market leader. They have several packages. They have Maxwell, which is electromagnetic analysis, and then there is MotorCAD, which is one of their latest tools that came out with a multiphysics analysis embedded into one software package. So as you can see, it has electromagnetic analysis, thermal analysis, mechanical, structural analysis, and then a lab environment where you can dive into the results, post-process the results, etc. And then Mentor Graphics or SimCenter MotorSolve is another most famous motor design software. I think they have evolved pretty much very well. I think you have capability to export the models that are designed in MotorSolve and do multiphysics analysis as well. JMAG, I think, is coming up pretty well. They have several customers now who use their software to do electromagnetic analysis, particularly. Siemens has Speed. MATLAB Simulink is another numerical analysis tool. So you need to know a little bit of MATLAB coding and just to identify the components that are available in MATLAB Simulink to design an electric motor. You can design DC motor. You can even design a power electronic circuit that operates the motor design you have come up with. But this is more related to the numerical design. And then Altair Flux Motor is one of the commercial software that is available for, as you can see, Flux. It's mostly designed for electromagnetic analysis when you start designing an electric motor. So let's say if I ask you, or if somebody asked me to design an electric motor, right? So this is the workflow that I would follow. So I would start with sizing. So let's say you're given an electric bike. You're asked to design an electric motor that works with the electric bike. So it has to be in wheel. So the first thing you think of is looking at the outer dimensions of the motor, and then you look at the inner diameter because you need to have some space left inside so that you can have a shaft that connects the wheel to the motor, right? So and then you look at the overall volume that you have available. So you only have that tire size volume that's available for you to design this electric motor. So once you have sizing information, then you apply motor sizing equations, which will determine the load torque. Let's say it's designed for 200 or 250 pounds of weight. So you determine the load torque that needs to be handled by the electric motor that you're designing. And then you look at the torque speed characteristics. Let's say you're going at 50 kilometer per hour, which is exaggerated, but let's say you want to go 50 kilometer per hour on an electric bike. You need to have so much torque that is applied at different sample points on the speed. And then you look for input power and then the efficiency that you can generate when you're designing this electric motor and how it's being applied practically on an electric bike. Once you have your specifications ready, you start laying a CAD design. That's where some mechanical engineers come into the play. They start helping us out with designing a CAD model of the electric motor with stator, rotor, and how different dimensions should work. So once they give you kind of a rough CAD design, you can import that CAD design into the FEA software, like ANSYS Maxwell, for example. And then you start doing some electromagnetic analysis simulations and multiphysics analysis. While you're doing some finite element analysis, you can also do some numerical analysis. So finite element analysis is not absolutely perfect. It's just a simulation of your motor design. So numerical analysis will give you a little more practical results, but it takes more computation effort. You have to put in a lot of time to develop code for that numerical analysis. But if you can kind of design basic level of equations, then you can compare your performance of FEA model with numerical analysis before going into the next stage, which is optimizing the design. So once you have a good finite element analysis model, so yeah, once you have a good CAD design and FEA design, then you can optimize your design for maximum torque, minimum torque pulsations, put in higher efficiency as a constraint, and then you want to have as low copper losses, iron losses as possible in your design. So you add all that constraints to your optimization algorithm, and then you optimize your design. So the minute details, for example, the slot width or the rotor flux barrier width, they can be optimized using all the algorithms that you can develop. And then you go back to your finite element analysis, do an iterative analysis. Once you have a good optimized design, you can prototype that design and then you test it at different loads. Usually the motors that are available can withstand 100 to 150% of torque overload. So you would rather test your motor design once it's fabricated as an alpha test and a beta test before releasing it into production. But the most important thing is CAD and optimization. That's where most of the time is spent. You would look into, once you have a FEA design, you go back to optimization. Based on the results you get from optimization, you go back to FEA. Several iterations are done here when you're designing a commercial motor. So that's how a good electric motor will evolve out of your design phase and then be ready for your prototyping stage. So let's say this is an electric motor. That's how an basic electric motor would look like. And then you have the main components such as the housing, end plate, and the motor shaft. Also, the most important thing is the nameplate that has a serial number and the power rating and all that stuff. So let me kind of dissect that a little bit to remove each one so that you can see what's inside. So what's inside is pretty much steel. You have a rotor and then a stator. And then stator has coils, anything that is not moving, right? So it has coils that carry currents, which develop a rotary magnetic field. And then rotor has, if it's a permanent magnet motor, it has permanent magnets in it. So they develop their own magnetic field. Stator has their own magnetic field. Eventually, they both lock in to develop a rotating magnetic field that will rotate the rotor. So that's a basic principle of electric motor design. So if you look at a 3D model, that's how it would look like. So you have the stacks of rotor or stator, and then you have coils of, let's say if it is a 3-phase, you have 3 different phased coils like ABC or XYZ, you can say. So I'm going to cut that into half so that you can see the cross section of it. So if you're looking at the cross section of the electric motor, that's how it would look like. And this is obviously an FEA design based on a CAD design. So this is a three-phase motor. So that's why you have A plus, B plus, and C plus, and then A minus, B minus, and C minus, which would mean that the B plus is kind of going in, the coil is going in, and then it's coming out here. So similarly, the B plus is going in and coming out here. The reason they're alternating is to develop that rotary magnetic field. So when you're energizing these coils, they energize in a particular sequence so that the magnetic field that is developed will generate a rotating magnetic field that will rotate the rotor inside. So the stator slots and coils, that's one of the most important dimension that you need to optimize. You cannot take too much space, but at the same time, you have constraint of space. And then you have rotor shaft location. That's where your each and every design is different. So based on the shaft location, your inner diameter will change. And then you have your rotor. And then you have flux barriers are nothing but air gaps that are induced in the rotor, so that they'll kind of create a reluctance path for the flux that is flowing in. It develops a reluctance torque that adds on to the permanent magnet torque. I don't want to go too much in depth into math in this presentation, but the idea is to, when you optimize these flux barriers, you get an extra torque that adds on to your permanent magnet torque. So those are the red ones are your permanent magnets. Most of the permanent magnets that are available out there are mostly rare earth, like neodymium based or dysprosium based magnets. These are the main physical components that can help design your electric motor in a good way. The other most important thing is the air gap. Electric motor is essentially a kind of a transformer. So the air gap plays a really important role in determining how the flux is flowing between stator and rotor. So optimizing the flux barrier end shape there, stator teeth there, and the rotor dimensions will play a huge role in determining how your rotor and stator are saturating with magnetic flux density. You cannot have each and every material has a BH curve, right? So you cannot exceed the limitations that are given for the material itself. So that is the last crucial component that you need to be very careful of when you're designing an electric motor. Mostly cross sections will give you a better idea on how to optimize these. So moving on to finite element analysis. So let's say you have this model. Now you want to do finite element analysis on it. So there is some pre-processing. So pre-processing is setting up the magnet like north and south poles, and then setting up your coil directions and all that stuff is called pre-processing. And then you have Fes Solver. Once you run Fes Solver, you get the finite element analysis results out of it. I'll explain a little more on that in the next slide. And then once you have the basic results, you start post-processing them. So the post-processing is organizing your results, doing analysis on your results in such a fashion so that you have the efficiency results or torque versus speed at different speed locations, and all that stuff is called post-processing. So what happens in the solver, right? So it starts with discretization of a model, which means dissecting the model into really small components. And then these small components are called finite elements, which can be called triangles in Maxwell. Then you mesh the model with these triangles. You keep the most crucial components of the design as densely meshed as possible, so that the results of solving Maxwell equations at these dense nodes yield you the best results. So this is a electric motor that is kind of 1/8 of an electric motor, because most of the times to solve the complete motor design will take significant amount of time. So we could we could kind of use the symmetry theory and just cut the motor by 1/8, because this is a, I think, 48 slot, 24 pole electric motor. So we could applying symmetry can be we can cut down the motor to 1/8 of its size. So whatever results we get here, if you multiply that with 8, you get the final results, right? So that's how you save your computation effort. So you can see that the locations that are really important, you can see that they have higher density of the triangles or the mesh. This is the meshing part. That's what FEA does for you. You can apply different meshing technologies so that your crucial components of your models are solved accurately, and that's how your results match with your final prototyping results. So I have Fes Solver do initial meshing for me, and then I apply electromagnetic analysis to it. We want to kind of give you different components that are shown here. So it starts with a boundary. So apply a physical boundary for your model, and then you have your stator, you have stator slots, and then stator coils. That's why these this could be A phase, that could be B phase, and that could be C phase. And these coils are aligned such a way that this would go in and this would come out. So that would generate an electromagnetic field. And then your magnets are aligned such a way that they have north and south poles that generate field that interacts with the stator magnetic field. So you can see the arrows. That's your magnetic flux right there. And then you can see the actual value in Tesla. So once you have stator coils, then you have magnets, then flux barriers again. The dimensions of the flux barriers are determined in such a way that your torque pulsations are reduced, but at the same time you get higher torque because it adds a reluctance path to your model. And then you have the rotor, and then magnetic flux density is just magnetic flux per area. So you can calculate that once you have the final results. So that's a good electromagnetic analysis result, which can be interpreted as that's designed properly. And you can see the rotor has moved. I think we have applied a time of 1/10 of a second. In 1/10 of a second, you can see that rotor has moved that much because the electromagnetic field or electromagnetic analysis worked properly. So multiphysics analysis. What is multiphysics analysis? You know, as an electrical engineer, I think you're comfortable understanding electromagnetic analysis, but out there commercially in the industry, they want the motor design to withstand structural, the motor should have a structural stability. So you start applying structural analysis to the model that you design so that you can look at von Mises stress in megapascal. So you rotate the rotor at your rated speed based on your specifications, and then you look at your results here. In ANSYS Workbench has a good tool for doing structural analysis. I know other softwares have their own multiphysics components that can be used to do structural analysis. Once you have structural analysis and you think your motor design is structurally stable, then you apply thermal analysis. So you could see that the coils are the ones who has stator currents flowing through them. So they are the ones who develop more heat, and then they get dissipated into the stator steel to the rotor. If a motor is run continuously, you can see that the motors can go up to like 80, 90 C. So it is really important to do thermal analysis on your electric motor design so that once you have your motor into production, it doesn't fail because it has an over temperature fault or something like that. So I did talk about using MATLAB Sim-Lync to do numerical analysis. So when you look at numerical analysis, it's pretty much you have 3 phases of currents, right? So if you have a 3-phase motor, you have IA, IB, and IC. When you project them into 2 phases, you have D and a Q. So D is direct axis, Q is quadrature axis. The reason we do that is solving 3 axes can be complicated, but solving 2 axes can be much simpler than that. So you project your three axes into two axes, and then I think this is called a part transformation, which converts three axes to two axes using some trigonometric functions. Once you have that, you should be able to use these two axes and represent your motor design using a magnetic equivalent circuit. So you have reluctance paths in your motor design. As I said, the flux barriers add some reluctance to it. Magnet is a flux source, and then stator has flux sources which are developed by stator currents. Obviously, basic electromagnetic theory. That's how the flux is developed when your current is flowing through it. So you come up with your magnetic equivalent circuits, and then you can solve them in MATLAB, and then eventually the result that you're going to get is equal to uh, the finite element analysis that you're going to get. So it's just two different ways of solving it, but numerical analysis can be more accurate, but more time consuming too, because you have to solve all the equations by yourself or using MATLAB. So that's the theory or technical part of the motor design. So if you look at the industry, there are several different groups in which engineers go into this field. So I'd like to start with design engineering. So you'd start as a basic design engineer if you're an entry level engineer, right? So you have some motor design experience, you have maybe knowledge of MATLAB and ANSYS Maxwell. You start as a design engineer, and then once you have at least 2 to 3 years experience as a design engineer, then you would jump into project engineer, because in 2 to 3 years you're expected to jump into the project, lead a team, maybe just talk to vendors, suppliers. You have a good Rolodex in your hand so that you can handle a project all by yourself. So that's how you become a project engineer. And once you spend again 2 to 3 years as a project engineer, it can be faster than that depending on the company size. You become a project manager, because now you have almost like 6 years of dealing with the same projects in the same product line. So you become a project manager. But all this is about designing new products, handling the existing products in a company. While you design the products, there is another team of engineers who will work with you. They can be called product specialists. So what they do is they understand the design, they know exactly how to operate your design and present your design to the customer. So this is what product engineering would do. They're still engineers. They have design experience probably, but the idea is they can talk to the customers, explain the design in such a fashion that it would solve the customer pain points, so the customer is attracted to the buy the electric motor, for example. So once you are a product specialist for a few years, then you become an applications engineer. So it'll give you more autonomy to present the motor designs or motor drive designs to customers and explain their features, how they operate in specific applications. Going into senior level positions, once you become a project manager and stay there for like 2 to 3 years, there is a chance you could become an engineering manager, right? So now you'll be handling several project engineers, several design engineers will be working under you. You manage different projects and how they're operated, timelines, and all that stuff. One step above the engineering manager will be general manager. He will be the medium between the engineering group and the executive management. So any executive level decisions, for example, like changing the company path towards a different product line. So a general manager will take that pressure, kind of help engineering managers to divide the work among the project engineers. On top of general manager can be director of engineering. Obviously, he is in the executive level, so he'll be part of managing finances, how many funds would each engineering department would get, how many different product lines exist, and then determining all the resources and all that stuff. At the same time, on the other channel, product engineering, there'll be applications manager. Applications manager will schedule customers to talk to application engineers and learn about products. What are the new features that are being offered in the motor designs, etc. Once you have applications manager, then you have a product manager who will work with director of engineering and general manager, so that whatever the executive level decisions that they're taking, he'll be part of that. He will contribute to that based on what customers want. So he's a medium between sales and customers, and then engineering. If you go to executive level, I think at this point, everybody reports to VP of engineering, vice president of engineering, and then there is CTO who will take strategic decisions to move the company in a way such that they're developing innovation or innovative technologies. And then on top of CEO is pretty much CEO. There are chances that product management team can be reporting to vice president of sales and marketing, and then he will be reporting to CFO. These guys are more interested towards customers and finances that can be developed by customer base. So they eventually report to CEO. So that's how the executive level looks like in most of the companies. So if you are trying to get into electric motor design jobs or design engineering jobs in electric motor designs, I think you should start with a graduate or higher level education in electrical engineering with research focus in electric motor drives. Publishing a few papers in IEEE won't hurt. That just gives you your profile a huge weight so that you can be the standout engineer when they start looking at different resumes. And then you need to have expertise in at least one of the finite element analysis tools, such as ANSYS Maxwell or JMag or MotorSolve. You need to have expertise in MATLAB Simulink. I think this applies to any electrical engineer. Doesn't matter if he is going into electric motor design world. Most of the electrical engineers should have experience with MATLAB. And then you need to have good knowledge on closed loop control systems, how position loop works, how torque loops works. You just need to understand how the control systems work when you put an electric motor into the application. And then expertise in power electronics will be a plus. This is just something that once you get into electric motor design, you will realize that just designing itself is not sufficient. You need to have some understanding on how to control it. And the way you control it is using power electronics. So that's where power electronics come into the play and will be given huge weightage if you have knowledge on it. And then analog and digital electronics is required for most of the EE jobs because you use so many sensors in this world. So analog, it could be analog signal 0 to 10 volts or 0 to 24 volts, or it could be digital 0 or 1 binary electronics. It could be a switch on and off kind of scenario. So you need to have that knowledge when you go into electrical engineering jobs. And then some programming experience will always be a plus. I know most of the mechanical and electrical engineers don't like programming much, but everything is moving towards software these days. You need to have some sort of programming experience. It could just be analyzing your results in Excel using some if-else statements. So some programming experience will always be a huge benefit to the profile. I'd like to end this presentation with a Yoda quote. He says, "Difficult to see, always in motion the future is." And I believe that the motion is always generated by electric motors in any field, and automation is possible at any level. Thank you so much.